Welcome to Mini Tutorials in Spectroscopy. Let's talk about NMR spectra. The NMR transition frequency of a nucleus depends on the magnetic field experienced by that nucleus. In a given applied magnetic field, not all atoms of a particular element will resonate at exactly the same frequency. The local magnetic environment of the atom within the molecule plays a critical role in determining the exact transition frequency. For example, induced magnetic fields arising from circulating electron density can enhance or diminish the effects of the applied magnetic field. Since electron density is determined by the chemical environment, this phenomenon is referred to as chemical shift. Transition frequencies are also influenced by proximity to other magnetically active nuclei. For example, consider the carbon-13 NMR transitions of fluoroacetic acid. If we proton decouple, we are only concerned about the interaction between the carbon nuclear magnetic moment and the magnetic moment of the fluorine nucleus, both of which have I equals 1/2. Applying an external magnetic field lifts the degeneracy of the carbon-13 nuclear spin states. It is the transition between these spin states that we measure with NMR. Now let's consider the effect of the fluorine-19 nucleus. If its spin is aligned with the externally applied magnetic field, the carbon-13 nucleus experiences a stronger field, and its spin states are further separated. If, on the other hand, the fluorine-19 nuclear spin is antiparallel to the external field, the effective magnetic field experienced by the carbon-13 nucleus is reduced. Statistically, half of the carbon nuclei are in reinforced magnetic environments, and half are in the reduced magnetic environment. Thus, the carbon-13 transition appears to be doubled on the NMR spectrum. Note that the frequency differences between the two lines of the doublet is a measure of how strongly the carbon-13 and fluorine-19 nuclei interact. Let's examine the proton and carbon-13 NMR spectra of acetaldehyde. The proton decoupled carbon-13 NMR spectrum is an excellent example of chemical shift. Here we have two carbon atoms, each in different chemical environments. Owing to resonance and inductive effects, the carbon of the carbonyl group exhibits a large chemical shift compared to the carbon of the methyl group. Similar arguments can be made concerning chemical shifts for the proton NMR spectrum. Here, however, we also have additional information in the form of peak intensities and splitting. Owing to the fact that there are 3 hydrogen nuclei in the methyl group chemical environment, compared with only 1 in the aldehyde environment, the methyl group proton NMR signal is 3 times more intense. Closer inspection of the aldehyde proton signal shows that it has been split into a quartet by interacting with the 3 equivalent proton spins in the adjacent methyl group chemical environment. Similarly, the methyl group proton signal has been split into a doublet owing to the interaction with the aldehyde proton. I hope that you have found this short video on NMR spectroscopy useful. See you next time.